Hello and welcome back to the AI Research Roundup. I am your host, Alex. Today, we're diving into a paper from Essential AI called Practical Efficiency of Muon for Pretraining. The authors propose a new training method, or optimizer, called Muon. Now, an optimizer is the engine that helps a model learn, and Muon is a special type called a second-order optimizer, which helps it learn more efficiently. The key takeaway is that Muon can train models faster and with less computing power than the current standard, AdamW, especially when using very large batches of data. And for those of you who want to try this out yourselves, the team has put up a GitHub repository with the code. It's pretty straightforward. You'll find the core implementation in a muon.py file. The README is also really helpful, showing you how to apply Muon specifically to the hidden layers of a network, which are just the middle layers where the model does most of its complex learning. Alright, so to really see what this efficiency looks like in practice, let's look at the first figure. This chart plots the number of devices used for training. That's our computing power on the vertical axis, against the total time it takes in hours. Both optimizers, Muon in orange and AdamW in blue, are trying to reach the same performance goal on a Python dataset. What we're looking at is called a Pareto frontier, which represents the set of best possible trade-offs. You can see the orange line for Muon is always better. It's below and to the left of the blue AdamW line. This means Muon can either finish the training faster with the same number of computers, or use fewer computers to finish in the same amount of time. It effectively expands the set of optimal choices. And this next set of charts really drives that point home. We're looking at the same kind of Pareto frontier plot, but now across two different types of data. The top row is for the Python dataset we saw before, and the bottom row is for a general web text dataset called DCLM. Each column represents a different performance target, or loss threshold, measured in a unit called NATS, which is just a way to quantify the model's error, where lower is better. Across all of these conditions, the result is the same. Muon's orange line consistently provides a better set of compute and time trade-offs than AdamW, showing this efficiency advantage is really robust. So, why is Muon so much better at this trade-off? These charts dig into the reason, and it's all about data efficiency. The top row plots the token ratio. This measures how many more data tokens, like words, AdamW needs to see, compared to Muon to get the same results. A ratio above 1 means Muon is better. And you can see as the batch size increases along the bottom, Muon's advantage generally grows. The bottom two rows show this as a raw number, the billions of extra tokens AdamW needs. This extra data cost is surprisingly consistent across different model sizes, which is what gives Muon its stable performance edge. And this conceptual diagram really helps visualize why that token ratio metric is so useful. So on the left, we see a typical performance curve. As you make the batch size bigger, training is efficient up to a certain point, which is called the critical batch size. After that point, you hit diminishing returns and need more and more data. The key insight is on the right. Both optimizers have a critical batch size, but Muon's is significantly larger. This means there's a whole range of batch sizes where AdamW has started to become inefficient, but Muon is still scaling perfectly, which is why its advantage grows so much in that region. Okay. So we've established Muon is very efficient, but a huge practical challenge is finding the right settings, or hyperparameters, to make it work. This is where a technique called maximal update parameterization, or MUP, comes in. Maximal update parameterization provides a set of rules to automatically adjust key settings as you scale your model up. This means you can find the best learning rate on a small model and reliably transfer it to a huge one. This table shows those exact rules. You can see it sets different formulas for initial weight values and learning rates based on their location, whether they're input, output, or hidden weights. The rules use the layer's size, its fan in and fan out, which is just the number of connections coming in and out, to get the scaling just right. This makes tuning Muon for massive models much more manageable. But even with a great starting point like maximal update parameterization, there can be small errors that build up as models get bigger. So to handle this, the researchers developed what they call a telescoping algorithm, which is what we're looking at in this 3D plot. Here, we're searching for the best learning rate and weight decay, which is a setting that helps prevent the model from overfitting. You start with a wide search on a small model. That's the big top layer. Then, you zoom in on the best region and repeat the search on a slightly bigger model. The stacked layers show this process, telescoping in on the optimal settings, which you can see stay very stable. This approach makes finding the perfect settings for a giant model much more efficient. Alright, so after using these sophisticated methods to find the best settings, what does the final performance look like? These charts show a direct head-to-head comparison for a 1 billion parameter model. Muon is in blue, and the standard AdamW optimizer is in red. On the vertical axis, we have the training loss, which is measured in nats. Basically, a score for how well the model is predicting the data, where lower is better. The top row plots this loss against training steps, and the bottom row plots it against real-world clock time. And the result is really clear. Muon consistently achieves a lower loss, meaning it learns more effectively, both per step and per hour. Even at the end of training, as you can see in the zoomed-in plots on the right, that performance gap remains. At the end of the day, the evidence is pretty compelling. The Muon optimizer, when paired with clever tuning methods like maximal update parameterization, really does offer a significant boost. It's not just about achieving a slightly better score, it's about making the entire process of pre-training massive models faster and more efficient. This research helps push the boundaries of what's practical at the largest scales. That's all the time we have for today. Thanks for tuning in to the AI Research Roundup, and I'll see you next time.